Okay, so, all right, so. Okay, so virtual work principle. Okay, again, you know, at one level, this is a very deep subject, right? But I don't want to make it too deep here. So let's just keep things simple, okay? The text is going to have some sort of involved discussion on this concept, but we just want to sort of, you know, get to a point where we can use this principle, okay, to solve our original problem, okay? All right, so first thing we want to think about is work. Okay, so what's work? Work is, you know, at its most intuitive level, force times distance, right? Okay, so this we all learned in high school probably, right? Okay, so how much work does a force do? Well, you multiply the force by the distance that, okay, that the object that the force is being applied to moves. Okay, that's a rough idea of work. You can be a little bit more sophisticated about it. Okay, so work, you can also express this in integral form. Okay, so if we have some rigid body, okay, and a force is being applied to the rigid body moves, okay, with a certain velocity, linear velocity and angular velocity, okay. Force may also generate a moment, okay. So in that case, we write the work as force times velocity, or force transpose times velocity, plus the moment times the angular velocity, okay, and we integrate it from some initial time t0 to some final time t1. Okay, so if we ask the question, what is the work being done by this force and moment applied to this rigid body, which moves from this configuration at t0 along this path to some other configuration at t1? Okay, so you would use this integral formula, okay, to calculate the work. Okay, so that's the idea of work. Okay. Now, if you want to do calculation in terms of specific coordinates, okay, you have to choose a coordinate frame. Right? So you could put a B here, for example, the body frame. So let's do that. Okay. Now, those of you who've taken statics and dynamics probably know what the virtual work principle is, right? It's a very powerful idea, okay, that you can use to solve static analysis problems, okay, where you have complicated systems, okay, that is rigid links connected to each other by joints, robots, okay. So the basic idea is, okay, so let's start with virtual work. Okay, so if you have, so the first thing that's required in order to apply the virtual work principle is that things have to be in static equilibrium. Okay, so assuming static equilibrium, okay, so nothing's moving, right? But forces and moments are still being applied, okay? So they don't do any work. Now we're going to pretend that they do a little, like this virtual work. Okay, so we're going to imagine that over a small interval of time, delta t, okay, we're going to calculate the work. Oops, sorry. FB transpose plus So we're going to do that. Okay, and now I'm not following the principle that I told you guys to follow, right? And that is, let's think six-dimensionally. Okay, so here I am writing things the old-fashioned way. Okay, I told you don't do it. Here I'm doing it. Okay, so I'm going to fix that. Okay, so let's write this as T0 to delta t. Okay, let's write this as FB transpose times V sub B dt. Okay, so there's my work. Okay. All right, now, this is useful for systems. Okay, so let's say we have, okay, so here's my system. Okay, and it's in static equilibrium. Nothing is moving. Okay, nothing is moving. And we have torques, tau 1, say tau 2. And we have forces being applied. Okay, so maybe we should draw the force in the other direction. Okay, it's the reaction force from the wall. Okay, so the principle of virtual work says, well, one way to say it is that the power in equals the power out. Okay, so in this case, power in is the power generated by the torques, tau 1 and tau 2. Power out, the force is the output. Okay, so it's the power generated by this tip force F. Okay. Now, if we use the virtual work principle, okay, to express that fact, what we end up with is that we can now write this. Okay, so this is from the perspective of the output. Okay, the force generated at the tip. So that will be F sub B. Okay, now let's also write this from the perspective of the input. Okay, from the torques. Right, so this would then be T0 plus delta T. This would be the torque transpose, okay, times the joint velocities. Theta dot dt. Okay. All right, so now this has to hold for any arbitrary virtual displacement VB times dt, or virtual displacement theta dot times dt. Okay. All right. So above holds for any. Okay. Well, first of all, for any interval. Okay. And also, okay, also for, okay, any virtual displacement, any virtual, and this is an infinitesimal displacement. Okay, V sub B dt. Okay, and theta dot dt. Okay, all right. So what that implies is that the integrands have to be the same. Okay, it implies that FB transpose times V sub B is equal to torque transpose times theta dot. Okay. All right. So what can we do from here? Well, now we use the Jacobian relation. Okay. We say that since v sub b is equal to j sub b times theta dot. Okay, let's put that in there. We will get fb transpose j sub b times theta dot is equal to tau transpose theta dot. Okay, and remember this has to be true for any virtual displacement theta dot t. Okay, so that implies that fb transpose jb equals tau transpose. Okay. Or tau equals jb transpose times f sub b. Aha. There it is. So finally the answer to our question. Okay. So given this situation, we have some force applied at the tip. Okay. What are the input torques necessary for the robot to be in static equilibrium? Okay, there it is. Okay, we see it's the Jacobian. More specifically, it's the Jacobian transpose. Okay, so contrast that with this. Okay, so V is Jacobian times theta dot. In the static case, we have the input torque, joint torque tau, is J transpose times F. Okay? All right, so now you can answer this question. Right? Okay. Well, what about if we want to use a space Jacobian? Okay. Well, suppose we want to write, okay, well, V sub s is add TSB VB. Okay. And J sub s is add TSB J sub B. Okay. And F sub s is, what is it? Add TBS transpose F sub B. Okay. So we can put all these things together. Okay. And we can now rewrite that bottom equation in the following way. So tau is equal to, okay, JB transpose, which is, well, I probably should have written it the other way. Okay, let's write it. JB is add TBS JS. Okay, so this is add TBS JS, the whole thing transpose, times F sub B. So I probably should have written this the other way. Let's do that. Add TSB transpose F sub S. Okay, so times add TSB transpose times F sub S. Okay, let's clean this up a little bit. So this is J sub S transpose times add TBS transpose. Okay, and this is add TSB transpose F sub S. Okay, and then you can see that something's going to happen here. Okay, JS transpose. Okay, so this is add TSB times add TBS. Okay, the whole thing transpose times F sub S. All right, so this cancels. Add TSB times add TBS is equal to the identity. All right, so we're left with is JS transpose theta times F sub S. Aha, so that's consistent. Okay, so tau is equal to that, is equal to J sub B transpose F sub B. Okay, so as long as they're consistent, we'll just write it this way. All right. Okay, so the formulas are, you know, if you look at the derivation, they're involved. Okay, but you see that in the end, okay, it's a very nice, they reduce to rather simple form. Okay, and there's a nice consistency to all the notation, right? J sub B times F sub B, J sub S times F sub S. Okay, all right, so okay, so if I gave you 1, 2, 3, 4, 5, 6. Okay, some manipulator. Okay, and we applied some spatial force F. Okay, some spatial force F, and let's say we have some joint torques tau 1, tau 2, up to tau 6. Okay, so I asked you, so I'm applying this force at the tip. I want the robot to be stationary. I want the robot to be in static equilibrium. What should my input torques be? Okay, what should my input torques be? And you say, aha, well, that's easy. I just solved this. Okay. So if I'm pulling on this end effector, and I want the robot to be still, the torques that I have to apply are given by this. Right? Calculate the Jacobian at this posture, multiply by this spatial force F, and that's my input torques required to keep this robot stationary. Okay. Okay. Now I could also ask the other question, right? If I apply these joint torques, what's my force at the tip? Okay, what's my force at the tip? Okay, so given the torques, what's the force at the tip? And you say, well, okay, that's easy. And just do F is J inverse transpose times tau. Okay. All right. So, aha, you say, well, the inverse doesn't always exist. When does the inverse fail to exist? When the robot is singular. Okay, I'm going to go out and murder that person. Okay, so, right? So singularities come up here again. Singularities here, not good. All right, let me throw out one more example for you. I want you to think about. Okay, so 1, 2, 3. Okay, now I have a 3-link robot. And I apply torques. Tau 1, tau 2. Let's draw the arrows this way, tau 3. Okay? And it's going to apply some certain force this way. Okay? So let's just worry about the end effector force, not the moment. Okay? So let me ask the following question. Given that I applied certain torques tau 1, tau 2, tau 3, what is the force applied at the tip F? Okay, so what's the force? Given tau, what's the force? Okay, so for this problem, you would say, aha, well, let's see, x1 dot, x2 dot, okay? So we only care about positions. Is some Jacobian j sub theta times, right, theta 1 dot, theta 2 dot, theta 3 dot. Okay, so this suggests to me that this Jacobian is 2 by 3. Okay, so it's a 2 by 3 matrix. Okay, it's a 2 by 3 matrix. Okay. Now I also know from my very careful derivation here that I can write tau is equal to, well, let's write it out. It's tau 1, tau 2, tau 3, okay, is equal to J transpose, this Jacobian transpose, times F. F is now 2-dimensional, so it's F1, F2. Okay? J transpose F. Okay, so throw away the torque, the moment part, just worry about the force part. Okay, so the question I posed to you was, given T, my input torque, what's my F? What's my F? Right? Now, if I answer the other way, right? Given force, find the torque. That's easy. Okay? Just plug it in, calculate. You get it, right? What about the other way? What about the other way? Well, you have to think, well, does a solution exist? Right? And you say, well, it's 2 by 3, right? So 2 equations, 3 unknowns. Yeah, it could exist. In fact, there could be like an infinite number of solutions here. All right? Okay. Something breaks down here. Something breaks down. Okay? So what happens? Remember, this equation here only holds what? What's the assumption here? The assumption is static equilibrium. Okay, static equilibrium. The robot is not moving. Okay, it's static equilibrium. Now, if we apply a force, if we apply torques in this situation, okay, let's say this tip is pushing against the wall right here. Okay, is it in static equilibrium? That's the question you have to ask. Is it in static equilibrium? When we apply torques like this, are all the links stationary? Or can some of the links move? Okay, so think about it. Aha, looks like a 4-bar linkage, right? 1, 2, 3. Imagine this 4th bar. Looks like a 4-bar linkage. So if we apply torques, this is going to move. Okay, it's going to move. Okay, something like that. Okay, not a very good picture, but it's going to move. So it violates this static equilibrium assumption. Okay, so to pose this question, given torque, find the force F generated at the tip. Okay, this violates the static equilibrium assumption. Okay, now, if you want to consider the dynamics, then that makes sense. Okay, but it's not static equilibrium. Okay, so this doesn't work. Okay, so in this case, when the dimension of the torques and the dimension of the forces are the same, okay, that is when the Jacobian is square. Okay, when the Jacobian is square, okay, you can solve this. Okay, but anytime you have redundancy, okay, more joints than the end effector degrees of freedom, okay, you can only answer it in one way. Okay, given the forces, end effector forces, find the torques required to maintain static equilibrium, but you cannot go the other way. Okay, that's an important point. Okay, I think this is a good place to stop, so let's stop here.